So let's get started. We have a lot of interesting stuff to cover today. Now that you learned a lot of the basic building blocks, hopefully we'll be able to build a computer. Not all of it today, but really the principles are going to come today. And you also know that again, it's an optional assignment. You will get credit for this for 1% for reviewing Moore's paper. And more importantly, you will be informed about what Moore really said, as opposed to what everybody says what Moore really said, right? Okay, so this is what we're going to do today. We're going to start with the von Neumann model, which is a very influential model of how computing is done today, and probably going into the future. But people are trying to change that, including the research that we do over here. But this will stay for a long time still, and in some part of the computer still. So, okay, we'll talk about LC3 and MIPS as examples of von Neumann machines. We'll focus on LC3, so we're going to cover a lot of this book today, especially chapter 4, and we'll move into chapter 5 also. And we'll cover the instruction set architectures, and I'm going to give you examples from both LC3 and MIPS. LC3 is an instructional computer, Little Computer 3. MIPS is a real ISA that's used out in many set-top boxes, for example, around the world. Maybe it's not as popular as ARM today, but it's actually quite good for both instruction, and it's a real instruction set architecture. And we're going to talk about what that is, what they are. We're going to look at several instructions, and tomorrow we're going to do some assembly programming, so we're going to have some fun doing programming. We're going to actually look at machine code programming, and then we're going to look at assembly programming and look at subconstructs. And then next week, we're going to go into microarchitecture and different forms of microarchitecture. Okay, so these are the readings. So today we're going to cover chapter 4 and 5, especially Pat and Patel, but these are your readings. Hopefully you're doing the readings. It's important. This is a recommended reading. You don't have to do it, but I actually elaborate a little bit more what could be useful for you to do it. It's useful. Okay, and you can see that appendices A and C appear all over here, so it's good for you to do them. Okay, so this is what we'll cover, as I said. I guess I don't want to spend more time on it, and I'll just move on to the von Neumann model. Basically, we want to build a computer, right? We want the basic elements. We already have the lower level basic elements, transistors, logic gates, and all of those methods that we use to construct them. Now we know how to time them also. But now we're going to raise the level of abstraction a little bit, and we're going to talk about how to use them to build decision elements and storage elements that are actually useful for executing a program. So for a computer, we're going to cover the basic elements of a computer, and those consist of decision elements and storage elements. So to get a task done by a computer, remember when we started the lecture, we said, why do we need computing? We want computing to solve problems, right? To solve problems, you express the problem as a task. Task eventually gets translated into a program. So we want that task to be done by a computer. So we need the computer, we need data, and we need the program. So program is more formally a set of instructions to complete a task, and the instruction is the smallest piece of work that's done in a computer, at least from the programmer's perspective. If you go to the hardware design's perspective, of course, there's a lot of pieces of work. A NOT gate, it does a piece of work, right? But from the programmer's perspective, it's really the instruction. Programmer doesn't see anything underneath the instruction, right? As a programmer, as an assembly programmer, you see the instruction and you see the specification of the instruction, and you believe that the underlying hardware, underlying computer will give you the result of that instruction correctly. That's the contract. That's the hardware-software interface. That's why this is called the smallest piece of work in a computer. So small piece of work always depends on the abstraction level you're looking at, right? If you're at the transistor level, there's electrons are moving. Maybe those are the smaller piece of work. Okay, so basically we'll start building the computer. To be able to build something, you usually need a model so that you can get your head around it, right? You have all these building blocks, transistors, logic gates. What do you do with them? Like, how do you orchestrate all of that? So we're going to take von Neumann model as an example, and this is a fundamental model that was proposed by John von Neumann. Who knows the name John von Neumann? That's good. Hopefully everybody will know by the end of this lecture. And that's him. He basically built a lot of the principles of computer architecture. And this is the paper that we actually looked at, referenced in one of the slides. You don't have to read it. It's not an easy-to-read paper, but you see that it was written in 1946. And he and his co-authors defined the computer to be consisting of 5 parts: memory, processing unit, input, output, and control unit. And basically all of the computers today, we have all of these 5 parts. And the key thing is orchestrating these parts. So throughout this lecture and throughout actually most of the course, we will consider 2 examples of the von Neumann model, LC3 and MIPS, and x86, which is commonly used everywhere, ARM, which is commonly used everywhere. They're all examples of the von Neumann model. And I'm going to define what von Neumann model is as we go through. But this is an example of von Neumann model. Basically, you have a processing unit, which is the master of everything. It interacts with memory. And we're going to look at these different components. So your computer looks like this, right? Maybe the input-output devices are different today. Like you have touch screens, that's another input device. An output device may be the computer speaking somehow, right? But it's still input and output. Okay, so let's start with memory. You actually know what memory is, but now we're going to look at the higher level of memory, like from somewhat from the programmer's perspective. So memory stores data and programs. And in the von Neumann model, there's really no distinction between data and programs if you just look at memory. If you just observe the memory of this computer, you cannot tell what's an instruction and what's a data. In fact, a data element may be used as an instruction, and we will see that in a little bit, because there's no distinction between them in memory. Memory is a linear array. So it contains bits. Bits are grouped into bytes. Hopefully you know this. I'm going to go through this quickly. Bytes are 8 bits, and then bytes are grouped into words, or bits are directly grouped into words. And word is defined by the instruction set architecture, which is the hardware-software interface. We're going to look at that. It depends on your instruction set architecture. So how the bits are accessed determines the addressability. We actually talked about this. So you could have a word addressable machine. Basically, this specifies that your address indicates a single word. Basically, your address is for example, 32 bits. That's true in MIPS. Or you could have a byte addressable or 8-bit addressable machine, in which case your address indicates a byte. Address 0 is 1 byte, address 1 is the next byte, address 2 is the next byte, ... If it's word addressable, address 0 is for the first 32 bits, address 1 is for the next 32 bits, and then so on. Okay, so this is the programmer's perspective again. And the total number of addresses is the address space, how many addresses you have in the machine. And that's really specified by how long is your address register, if you will. So basically in LC3, the address space is defined to be 2 to the 16. It's a little computer. It's instructional, that's why it's so small, right? 2 to the 16 is not that big. And in MIPS, the address space is 2 to 32. That's a more realistic machine. So it's 32-bit addresses. It's byte addressable, so you can imagine that it's 4 gigabytes. But it's even small today, right? In x86-64, x86 evolved over the course of 40 plus years. Before it was not like this, but today in the architecture, they changed the address space to be up to 2 to the 48. And that's a bigger number than most memories are today. So as programs evolve, as people need more data, the address space actually increases also. So people actually change the ISA over time. Maybe not as fast, but they actually add more bits. Okay, so this is hopefully obvious. Okay, each data word, I said word addressable versus byte addressable. So let's take a look at that a little bit. If you have a word addressable memory, from the programmer's perspective, each data word has a unique address. In MIPS, as I said, a unique address is for each 32-bit data word. In LC3, which is in this blue book over here, Pat and Patel, the unique address is for each 16-bit data word. So it's basically the definition of the instruction set architecture. The person who designed the machine said, okay, I want this data word, and the software that's written on it should obey this fact, that I chose my data word to be 16 bits. Okay, this is an example, pictorial example. In MIPS, basically, word 0 has 32 bits. You can see the hexadecimal over here. You have 8 4-bits over here. And then this is the word address that you have for the data. This address 0 contains this word. Address 1 contains the second word. Address 2 contains the next word, and next word, ... Makes sense, right? Okay. So if you have byte addressable memory, then each byte has a unique address. This is different from this one. Here, we are not able to address each byte. You can see that, right? The address 0 is here. Address 1 is here. So the granularity is 32 bits. If you want to take a byte, which means that these bytes 8, 9 from here, you have to read the word and somehow extract those 8, 9s, that 8, 9 over here. You cannot directly address that byte. So people found that it's useful to actually address bytes. In fact, a very good example of this instructional LC3 ISA, Little Computer 3. Little Computer 3 in this book is really word addressable. But later, the instructor of this book found out that actually it's good to have byte addressable memory because people operate on bytes. Programmers need to use bytes because there are elements like pixels, for example. If you want to actually manipulate a pixel, that's a byte. And it might be good to just load a byte and use that byte. So later, the authors of this book extended the ISA or modified the ISA to become LC3B, which stands for Little Computer 3 Byte Addressable. So there's a byte addressable version of this, which is actually in Appendix A and C, which is required reading. Okay, so basically these things evolve also, but there's a good reason for having byte addressability because that really corresponds to the reality of how people want to manipulate data. If you're operating on bytes, it's good to have a byte addressable machine. If you're never operating on bytes, there's really no reason to have a byte addressable machine, but people find out that actually you do operate on bytes in real life. Okay, so MIPS is actually byte addressable for that reason actually. LC3B, which is the updated version of LC3, is byte addressable too. So what does that mean? That means that you still have the notion of words, but you address things based on the byte address. So you have the byte address of the word over here. This word starts from address all zeros. And then you have byte 0, byte 1, byte 2, byte 3. And then the second word starts from address 4, byte 4, byte 5, byte 6, byte 7. Next word starts from address 8, byte 8, byte 9, byte 10, byte 11. Of course, 10 and 11 are A and B, right? So on. Okay, that's the idea. Now you can actually address this word and just get 8, 9 out. Okay, so how are these 4 bytes addressed is an interesting question. So basically, this is the address of the word, all zeros, and we know that the next word should be 4 because there are 4 bytes in it. But then there is a convention that you need to follow somehow, which is 0 over here, right? So we're going to talk about that a little bit. In the end, it's not going to matter, but you need to know this to work. Basically, this is similar to the question of, is this the most significant byte in your 32-bit word? Or is this the most, so let's assume that your word is like this, and you assume that this is the most significant byte. So this is the least significant byte. So these are bigger numbers if you have a 32-bit word. You may address the most significant byte as address 0, or you may address the least significant byte at address 0. And these are 2 different conventions. I'm going to give you an example of that again. And MIPS happens to be little endian, meaning that least significant byte is addressed as word 0, byte 0 over here. Okay, so this is a convention, so I'll use Juan's analogy over here. There's a book called Gulliver's Travels, and there are 2 different ways of breaking eggs. Do you guys break eggs like this? These are eggs, right? There are people who break their eggs in the big endian way. Big endian is the part of the egg that's bigger, and you start breaking from there. So that's maybe more important. That's address 0 maybe. Or you can break your eggs from this side, which is the little part, right? So that's the little endian. Okay, this is an analogy basically. So this is a convention. There's no right or wrong over here, right? Clearly you can break your egg from the left or from the right and you will still get the same result. But you need to obey the convention in computers so that you can understand. So the big endian means basically the least significant byte has a higher address. That's what it means, basically. Address 0 corresponds to the most significant byte of the word, and the higher address corresponds to the least significant byte. And that's true on the second word, that's true for the third word, and that's true for the fourth word, etc. There are some machines that are big endian. Little endian means most significant byte has the higher address, higher byte address. So the most significant byte has address 3, least significant byte has address 0. You can see that that's true over here. Okay, so you'll deal with little endian machines. And I like little endian machines more because I somehow think this is more intuitive because this is least significant, so it also has the smaller address. But there's really no correspondence. This is really by convention, right? You could easily think this way also. Okay, so does this really matter? So it's really a convention. So for the purpose of this course, it will not matter, but you should know what's a little endian and big endian. But it might matter actually, whenever you're actually converting data from a big Endian machine and transferring data to a little Endian machine, you need to know the systems. So if one machine has this convention, and if the other machine has this convention, you should not take byte 0 over here, like the byte that's over here, and put it in the wrong location, right? You cannot put it over here. You cannot say this byte 0 address corresponds to address 0 over here, because that's not correct. You will need to reorder the bytes in a word. And this actually arises in real systems. If people are not careful, they'll get the wrong data, and for some time they'll have bugs, and eventually someone figures out it's a bug and you'll fix it. It's better not to get into that situation and know what your system is like. Okay. So there are two ways of accessing memory. We're now go into a little bit detail in terms of how you access memory. You can read from memory. This is also called loading, and you can write to memory. This is also called storing. And we've seen how to read and write in the circuitry of the memory earlier, right? Now we're thinking from the programmer's perspective a little bit. So internally, there are two registers that are necessary to access memory. This is good for our understanding, and your book uses this convention. So there's a memory address register, and there's a memory data register. So in order to be able to read from memory, you should put an address into the memory address register, and then wait for a while. And when the memory is ready with the data, it puts the data into the memory data register. And we will see this many times in this course. So to be able to read, basically step one is to load the MAR or MAR or memory address register with the address. And the memory magically responds with the data and places the data into MDR, memory data register. And you can read it from there. To write, basically there are multiple steps. You first load the MAR with the address and the MDR with the data, because you need to write the data. So you both load the address and the data that you're writing and activate the write enable signal. And memory at some point finishes it. So we'll figure out when the memory finishes and what you need to do after that in a later part of the course. But this is how it works basically. And we're still talking about memory. Okay, so now we're done with the memory. We're going to go back to it, of course. Now we're going to use instructions to actually trigger these actions. And they're going to be called load and store instructions. And they're going to have different types. For example, load byte, load word. That's why this is important to know. Okay, now let's go into the processing unit. Now we know how to load data, how to read data, and how to write data. Let's go into how to orchestrate this. So basically, processing units can consist of many functional units. Functional units are different units that can do different operations, basically. You can think of it that way. And it consists of many, many components like muxes, multiplexers. It consists of logic functions like NOT. And there's one unit that's very important, and this is covered, of course, in this book, but it's also covered in more detail in chapter 5 of the other book. It's called the arithmetic logic unit. So arithmetic logic unit is essentially a unit that performs arithmetic operations and logical operations. It performs an add, for example. It performs a NOT or XOR. It depends on how you design it, of course. Underneath, you can design to be very minimal. It could perform only one thing, but the programmer may write many things, and then you somehow make sure this works. Okay. Basically, in LC3, the arithmetic logic unit that you will see executes an add and NOT, and XOR also in LC3B, because that's a new instruction that was added. And MIPS, you will see that the arithmetic logic unit is able to do add, subtract, multiply, and NOR, shift left logical, shift left, ... You can see that. Different kinds of shifts, basically. And I believe rotates also, but you can, you'll see this, we'll get to it. Basically, ALU processes quantities that are referred to as words. So in MIPS, in LC3, we said that the word length is 16 bits, and in MIPS, it's 32 bits. But there are actually cases in other ISAs and in newer ISAs where you actually operate on smaller elements. So in the ALU also, you can operate on bytes, smaller granularities. Because people found out that you can actually be more efficient. If you don't need to use the entire 32 bits, why not actually operate on only the 8 bits, right? But assume that this is true for now. But there's nothing really special about this, right? You can operate on any granularity if you design your arithmetic logic unit to be able to operate on that. So we're going to see temporary storage registers. So the registers are temporary storage that the processing unit has to store some values to operate on. You don't always want to go to memory because memory is slow. You want to actually operate on what's called registers. This is a small file, register file. We saw the registers, right, earlier. You build basically multiple of those, and then you move the data from memory into the registers, and then you bring the data from the registers into the arithmetic logic unit, and then do the operation. So that's the idea. For example, if you want to do the calculation A plus B times C, you bring A into a register, you bring B into a register, you do the A plus B, store the result into a register, and then you bring C into another register, and then you do the multiplication of those two registers, store the result in another register, and then write the register back into memory. That's the idea. So a register you can think of as a very small memory space that's inside the processing unit. That's not part of memory. This is inside the processing unit that's close to the arithmetic logic unit, where you bring the data in from memory and you store the data temporarily. And also you store the temporary results as well in registers so that you can operate on things quickly. Because the register file is small, memory is big. Make sense? Yes. Yeah. Well, that's dictated by the program. That'll become more clear, but when you write the program at the assembly level, you will tell which register should get which data. This will become more clear as we go through. Yeah. Then there are registers. Well, you could potentially overwrite a register that you need. You could make an error, that's right, but as an assembly programmer, the instruction set architecture specifies how many registers you have and what are the registers. So you should obey that, basically. If you actually destroy a value that you really need, then that's your fault as a programmer. Okay. And of course, if people don't write assembly programs, you will learn about assembly programs here, but if people don't write, most people don't write assembly programs, right? Most programmers. So what happens? What happens is a higher level language gets translated into machine code, which is lower level than assembly. And it's the job of the compiler to do the allocation of the registers to particular memory locations. So people have automated this process. The compiler is the thing that does the register allocation. So this will become a little bit more clear, even though we're not going to go into the higher levels of the stack compiler or how to do the allocation. It's very similar to a programmer saying, okay, I want to store this data into a register. Now its program is replaced by a machine or code that actually compiles the higher level language program such that the data that's operated on is placed into the registers first. Okay, so let's talk a little bit more about the register. Well, I've already said this implicitly, but basically, why do we want registers? You could directly operate on memory locations, right? You could directly say A plus B times C. Now the question is, where do you store this? Well, that's one question. And also, memory is always slow, right? You don't want to go to memory all the time. So basically, registers are introduced to ensure fast access to operands. Operands are basically things that you operate on. And for formal definition, you should look at that, but this is actually very close to the formal definition. So typically, one register contains one word. There are exceptions to that in real life today, but we're being simple over here. Register set or register file is a set of registers, basically. So for example, this is the set of registers that's visible to the programmer, assembly programmer, or the compiler. So LC3, for example, has 8 general purpose registers, register 0 through register 7. So you have a 3-bit register number. So that 3-bit register number is encoded in the instruction, as we will see later, and that indicates which register the instruction is operating on. Okay, that's one example. In LC3, register size is the word length, which is 16 bits. MIPS has 32 registers. It's a more real ISA. So people found out that as you increase the size of the registers, it's good because you have a lot more values that you can bring into the register and operate on those values. For example, if you need to operate on 10 values, but you have only 8 registers, well, too bad, right? You cannot put everything into the register, so you need to go to memory once in a while to operate on those 10 values. That's why if you have a larger register file, you can keep more stuff, more variables, close to the arithmetic logic unit, meaning inside the processing unit, and you don't need to access memory as much, because memory is slow. Okay. For example, I think I'll give you another example. x86 actually started with 8 registers a long time ago in the 1970s. Now they have a lot more registers. I believe they have 32, but don't quote me on that. But basically, if you're going to write a program on a particular machine with a particular instruction set architecture, you need to know how many registers you have, as it will become obvious. So this is what you know as a programmer. So this is the MIPS register file written in an odd way. But basically, these are the register numbers. These are the mnemonics or names that you use in assembly language. You will see this a lot. So for example, register 0 is written this way, and it's actually tied to the constant value of 0, because people found out that that value is very important. You usually do operations on 0, so we should tie one register to just 0. Whenever you refer to register 0, you will get 0. Okay? There's a temporary register, but the interesting registers are somewhere over here, actually. So you get a lot of interesting registers. Okay, some of these will become more clear when we talk about programming. But you see that there are 32 registers, and their general purpose, they can be used for anything except for really register 0. Other registers you can really use for anything. Even though they have names over here, you can really use them for anything you want, as long as your program is correct. Except for 0, because clearly you cannot write to 0 some other value than 0. Because by convention, the machine always returns you 0 if you want register 0. Okay, so let's talk about input and output relatively quickly, because we're not going to focus a lot on input and output. Actually, in the remaining part of the course, we're going to focus a lot on the processing and control unit, and in the later, toward the end of the course, we're going to focus more on memory. But input and output, we're not going to cover a lot. But hopefully this is relatively simple. Basically, many devices can be used for input and output. They're also called peripherals, and you're using them every day. Keyboards, mouse, scanners, disks, they're all input devices. Some of them also could be output devices, right? Monitor, printer, for example, disks are output devices. And as I said, the screens can be input devices also, and also output devices. I guess monitor is like that kind of screen is a small monitor. Okay, basically in LC3, if you really want to know, we'll consider keyboard and monitor, but we're really not going to go into detail. This is mainly for your benefit, and you can read Appendix C for that. Actually, there's an input and output chapter that we're not going to cover because we just don't have time to do that. Okay, so I've covered input and output very quickly, but this exists, and hopefully you empathize with it, right? Because you have to have some sort of input. And actually, let me go a little bit more into that input. For example, when you do input, what happens is the data gets placed in particular locations in memory, and then you can read that location through the processing unit so that you can capture, for example, a value that you input on your screen, because the data that you input goes into some particular place in memory, and if the program is expecting something to come from the input, the program that's running actually will get that value. Okay, there are multiple ways of doing it, which I'm not going to go into. We can look at it. Similarly, if you want to put something into the output, the program wants to output something because it's computed something. Let's say it's computing, I don't know, the number of characters in a book. The input is the book. You read the different pages of the book into the memory. You do the computation, and the result is how many characters you have. And the result is going to be written into the monitor. So basically, you write into a special register in memory, and that essentially means that you're writing to the monitor. And the monitor itself then takes the data from that register and displays on the screen. So there needs to be machinery that accomplishes things like that. And clearly, this is very much dependent on the input device, as you can see, and the output device. But the way that they interact with memory is very similar. You can think of the input device writing stuff into some particular place in memory, and different input devices have different parts of the memory, potentially. And the output devices also having different parts of the memory, and you put the data into those locations, that means that it's going to be output to that device. Okay, it's a bit more complicated than that, but the fundamental principle is really the same. Okay, so, but we're not going to go into input and output. If you really want to know, the blue book has a lot of information. So now, but we're going to go into control unit, because this is really the master of everything. It's really the maestro that controls everything over here. Basically, if you can think of the other parts of the computer as the orchestra, this is the maestro. It's the conductor of the orchestra, right? Okay, so basically what does it do? It conducts the step-by-step process of executing a program, or more specifically, every single instruction in the program. So to be able to do this, it needs to keep track of the instruction that's being executed currently, which we're going to call that location that stores that as the instruction register. So we're going to bring the instruction into that location, and the instruction will be there, and we're going to specify what the instruction is in a little bit. And you need another register that tells you what is the address of the instruction that you're executing currently, or where should you really get the instruction from. So this is called a program counter or instruction pointer. This is basically the address of the instruction. It points to the memory location that contains the instruction. So the first thing that happens in a machine is the machine gets loaded with an instruction pointer that points to the beginning of the program. Okay? And there's circuitry in the machine that we will see that goes and loads the instruction, the word, 32 bits in MIPS, 16 bits in LC3, into the instruction register. Now you have the instruction inside the instruction register. Now the machine can figure out what that instruction is supposed to do. So when you write program as an assembly language programmer, you're really writing those instructions, set of instructions, and the machine is starting from a particular location, a known location, so that you could get the beginning of the program, and then basically it will take that instruction, bring it into the instruction register, decode it and execute it, and then go to the next instruction. So we're going to see all that machinery, but we're going to talk about instructions first. So okay, basically I've defined what's called programmable visible architectural state. So whenever you program a machine, you know that there's some memory in it. The memory is the array of storage locations. It's indexed by an address. You know that it's word addressable or byte addressable. You know the address space. We've already discussed this. You know that there are some registers. These are giving special names in the ISA. And they could be general or special purpose. Assume that they're all general purpose. You can use them for anything, but you saw one special purpose register, which is R0 in MIPS, right? It's always 0. That's very special purpose. And a programmer also knows the program counter. That's the memory address of the current instruction. And basically instructions and programs specify how to transform the values of the programmable visible state. An instruction is really essentially a transformation that you do on this state. Actually, if you look over here, you don't see the instruction register, right? The instruction register is hidden from the programmer. The programmer doesn't know what that is. The programmer knows which address is the current instruction that's executing at, what is the state of all memory, and what is the state of all registers. And you write your program so that you transform the state of all of this to some other state, such that you get some useful work done. And useful work depends on the task you're trying to execute, and you write your program such that you achieve that task, right? So you select your instructions, select the set of instructions and sequence of instructions, and a way of sequencing through those instructions so that you can achieve the goal. Okay, that's very important. So this is what's visible to the programmer. But we're going to see a lot of stuff underneath that's not visible to the programmer that ensures that what I said is done. Okay? Instruction register is one very simple example that's not visible to the programmer. It's visible only at the machine level, and the machine basically takes the program counter, indexes memory with the program counter, gets the word in that location, places that into the instruction register. Now you have the instruction captured in a register. You can actually figure out what it is saying. What is the command, basically, that the machine should do? Okay, and von Neumann model is all about that, basically. You go through these instructions. You go through, basically, your program is stored in memory, and you have a way of going through those instructions one by one, sequentially. So there are two key properties of the von Neumann model. Aside from all of this, there are two key properties. Your program is stored in your memory, and you have a program counter or instruction pointer that sequences through the instructions in your program. Okay, this is also called a stored program computer, which means that basically instructions are in memory. It has two key properties, as I said, stored program in memory and sequential instruction processing. And these are both important, but this is going to be very, very important as we go into other models. So keep this in mind because we're going to break this at some level later on. Okay, basically stored programming is instructions are stored in a linear memory array, as we saw, and memory is actually unified between instructions and data. So the interpretation of a stored value in a memory location depends on the control signals that we will see later. So if the program counter actually points to a memory location, that means that you're going to interpret that memory location as an instruction. Make sense? Otherwise, there's no distinction between instructions and data. Of course, when you write and when you load, you think that you're loading instructions, but you need to make sure that the program counter points to it so that it's interpreted as an instruction by the machine. Okay, and the second is sequential instruction processing. Basically, one instruction is processed. As we will see later in this lecture, there's an instruction cycle, meaning what happens to process an instruction. It's fetched, executed, and completed at a time. So your program counter points to one instruction, the machine fetches that instruction to the instruction register, figures out what it needs to do, it executes the instruction, finishes the instruction, updates the memory or registers, depending on what the instruction specifies, and then goes to the next instruction. What does that mean? Program counter is incremented, or you basically increment it so that you go to the next sequential instruction. So as I said, a program counter identifies the current instruction. Program counter is advanced sequentially to the next instruction, unless you've explicitly inserted an instruction that says you should go to some other location in the program. Now, why might you want to do that? Because you might want to branch, right? You may have an if, then else statement in your computer, and now the next instruction that you execute is dependent on how that condition of the if statement evaluates. If it's true, the next instruction may be the next sequential instruction. If it's false, the next instruction may be somewhere else. Okay, we will see this tomorrow also, but please do the readings because it'll be a lot easier if you actually do the readings. Okay, but hopefully this is clear. You need to have a mechanism to map the higher level constructs like if, then else to instructions in the machine. And if you don't have an instruction that changes the control flow to some other place, you always go sequentially. Now I'm at address, let's assume that program counter is at address, I don't know, 8,000. The next cycle, the program counter will go to address 8,008. Well, sorry, 8,004. It's a byte addressable machine, right? So assuming that instructions are 4 bytes, words are 32 bits, the next instruction's address is 8,004. The next instruction, 8,008. The next instruction, 8,012, which is 800C, right? So basically, you advance sequentially. Okay, now we're going to go into a little bit more detail on the von Neumann model. I'm going to scare you with this picture, maybe. I don't know if you can see this, but all the slides are online before the lecture. So if you want to, basically, we're going to cover this machine. And we're going to see how the different instructions get executed on this machine. So this is an example of a control signal. So we're going to denote the control signals with empty arrows, white arrows. These are signals that control the operation of the MUX, for example. Which inputs should be passed to the output of the multiplexer? Or another control signal is load PC. Should the program counter be loaded with the value that's coming from the MUX out of here? Another control signal is ALU. What should the ALU be doing at this point in time? Right. So this is the entire machine. You have a register file over here, ALU over here, memory over here, input, output over here, and the control unit. So these are the 5 units in a von Neumann machine, as you can see. Processing unit, control unit, memory, input, and output. We're going to look a lot into this part, but we're going to interact with memory a lot, and you can ignore this safely for actually pretty much the rest of the course. But we're going to look at the operation here. Let me define some things. Control signal is one example over here. Data signals are denoted with shaded boxes like this, black arrows, black arrowheads. Memory, we know that it's 16-bit addressable for LC3. And MAR, which I mentioned earlier, is a memory address register. This is also not visible to the programmer, by the way. This is an internal register, so that you can take an address and put it over here, and you can get the data out of the memory, which is visible to the programmer. And memory data register is the register that gives you the data, or that you put data into so that you can write to memory. Okay, what else? Keyboard, we discussed monitor, but we can ignore that safely. ALU, in this machine, in this particular design, it has 2 inputs and 1 output because the instructions are that way. And you can see where the inputs are coming from. One input can be coming from the register file, another input can also be coming from the register file, but it could also be coming from somewhere else. This is not fully connected over here to simplify things. As we progress, you will see different parts of the connections. And if you really want to see everything, it's in the book. Register file contains 8 general purpose registers, as I said, register 0 through register 7. And none of them are hardwired to 0 in this case. LC3 doesn't have a register that's hardwired to 0. And the instruction register, that's the instruction register IR, as I discussed. So you have some address in the program counter. And the first thing that needs to happen in the machine is you have the correct address somehow getting over there. And once you have the correct address, what needs to happen is this program counter needs to be loaded onto this bus and put into the MAR, memory address register, so that you can get the data value out from memory. Memory brings the data into the MDR, and this needs to get loaded into instruction register. So you need to set the control signals appropriately so that this happens. And we will see how you set the control signals appropriately. But hopefully, this is called a data path, and there's also some control logic. But basically, this shows you the movement of the data. Data meaning some number of bits. So program counter needs to get loaded onto this bus and placed into the memory address register. And then you wait for some time, memory responds, the data appears in memory data register, and you need to make sure that that gets loaded into the instruction register. That's how you fetch an instruction. And we will see the step very clearly. Okay, so who orchestrates all of that? There's a finite state machine, which you know of. Well, we know of finite state machines, but there's a finite state machine that orchestrates all of that. This is really the control unit of the machine. And we will see how to build that later. For example, it tells the machine which ALU operation it should do at this point in time. That's dependent on what is the instruction over here, right? If the instruction is an add, this should say an add. If the instruction is a multiply, which doesn't exist in LC3, it should say a multiply. If the instruction is a not, which does exist in LC3, it should say a not. Right? And there are also things that we've seen before. These are tri-state buffers, right? These are the tri-state buffers that control the loading of a signal onto this bus or piece of wire that's of 16 bits wide. This is what you control to ensure that the data gets from one place to another place appropriately. For example, if you want to, that's the bus, that's basically the piece of wire. If you want to move the program counter from here into the memory address register, what you need to do is ensure that the gate PC is enabled. Remember, this is a tri-state buffer. If gate PC is 1, the input passes to the output. If gate PC is 0, the output is Z, floating, which means that this wire doesn't get connected to the bus, so the bus is not driven. So you need to ensure gate PC is 1, and you need to ensure load MAR is 1, meaning that you write enable the memory address register. So that's how you move gate PC, move the program counter value into the memory address register over here. But you also need to make sure that no one else is putting anything on the bus. Remember, tri-state buffers are that way. For example, there's a gate ALU signal over here. You need to make sure that no other wire is really driving the bus. So this has to be 0. There's another gating signal over here. This has to be 0. There's another one over here. This has to be 0. So there's only one bus. So you need to ensure that only one thing is driving the bus at a given time. Okay, so I've given you some examples of it. We're going to cover this in more detail. But basically, instruction and data are stored in memory, as I said. Typically, the instruction length is the word length, and the processor fetches instructions from memory sequentially. I'm going to repeat the one Neumann model. You fetch one instruction, you decode and execute the instruction, you continue with the next instruction after that. The address of the current instruction is stored in the program counter. Let me finish this and then we'll take a break. If you have word addressable memory, the processor increments the program counter by 1. That's how you go to the next instruction. This depends on your addressability clearly, right? Because if you have word addressable and your program counter is, then it's a word, then you increment the address by 1. If you have byte addressable memory, the processor increments the PC by the word length. So in MIPS, the word length is 32, and that means 4 bytes. 32 bits means 4 bytes. So you increment the program counter by 4. The next program, the address of the next instruction is the address of the current instruction plus 4. Okay, and in MIPS, they always typically set the PC to this value. That's the beginning of the program, basically. That's where all programs begin. Okay, so let's actually stop here, and then we'll continue after we return back. Okay, so let's continue with our instruction set architecture. So now we're going to get into instructions. But before we go into instructions, I'll give you the high-level overview. Oh, we already said this. So this is a sample MIPS program. We're going to see how to write this. You don't need to know about it right now, but in this case, you have 4 instructions stored in consecutive words in memory. Each of them is encoded with 32 bits. And this is an assembly program that you could write. It does something. You can figure out what it does. It uses the registers, as you can see. It uses things like this, addressing modes. It uses immediates, like -12, that's encoded in the instruction. This basically sets to register S3, write add an immediate value, -12, and store the result into register T0, right? And the machine code looks like this. If you know the manual, you can translate this easily to this machine code. This is basically the 32 bits that encodes this assembly instruction. So this gets stored in memory in a way that looks like this. These are the addresses. Remember, I told you that the OS sets the program counter to this location. It's a bit more complicated than this, but again, I'm giving you the very basics. Everything boils down to this fundamentals. There are layers of abstraction in between. But basically, program counter starts from here. That's the first instruction over here. And then it basically keeps going through the instructions. After this instruction is executed, you go to the next instruction, which is this one. After that's executed, you go to the next instruction. But basically, your program is laid out as instructions like this in memory. And you may ask me, why am I going from bottom to up? Well, I don't know. You could go from top down also, as long as your addresses are fine, right? This is a convention of looking at memory. It starts from 0 over here, goes to 2 to the 32 minus 1 up there. Okay, so basically no need to understand this now. We will get back to it, and we'll actually see how these are encoded. And these encodings actually get into the instruction register, and the machine interprets that instruction register so that it knows that you need to load word and compute the address based on this, and load the word at that address to this register. Okay, so basically the instruction is the most basic unit of computer processing. You can think of these as the words in the language of a computer. Instruction set architecture is a vocabulary. You can basically use different words to form many, many different sentences or programs, right? Or books, right? So the language of the computer can be written as machine language, which I showed you an example. Basically, this is a computer readable representation. This is binary, zeros and ones. Or assembly language, that's a human readable version of the machine language, essentially. You can directly translate from the assembly language to machine language by knowing the format or encoding of the instructions, which we will see. So we will look at 2 different types of instructions. One is the LC3 ISA, and the other is MIPS ISA. As I said, it's instructive to look at both because fundamentally they're very similar, actually. Fundamentally, even x86 is similar, but it's a bit more complicated. That's why we don't deal with x86 right now. So let's start with some example instructions. So there are 3 main types of instructions in any ISA. Operator instructions are instructions that execute in the ALU, arithmetic logic unit. So arithmetic instructions and logic instructions are like this. There are data movement instructions that move data from and to memory, basically either read from or write to memory. And there are also control flow instructions that change the sequence of execution. Not necessarily go from PC to PC plus 1 or the next program counter, but go to some other place in the memory to execute the instruction. So let's start with a simple thing. This is addition, right? This is high-level code. You may write this code in some programming language with 3 variables. Well, assembly is kind of similar, except this, we're going to put register names over here. Basically, add B to C and write the result into A. Add is a mnemonic to indicate the operation to perform. B and C are called the source operands. Remember, operands are things that the instruction operates on. In this case, you operate on B and C and do something to them, which is addition, and store the result into a destination operand, which is the destination A here. So this is basically the semantics of the instruction. Now let's take a look at how we map this instruction to registers. assume that you decided somehow that B should be in register 1, C should be in register 2, and A should be in register 0. That's how you do in LC3. We're going to get to that. But MIPS is not, it's basically the assembly convention. In MIPS, you basically call these $S1, $S2, $S0. I think this is a little bit more readable. That's why LC3 is a more instructional ISA, right? This is a little bit less readable, as you can see. Okay, so this is the assembly code in LC3 for that instruction, basically. You say add R1 to R2, store the result in R0. That's how you need to write the assembly if you want to do this addition. Now let's take a look at the encoding of this in the machine. So this is the instruction format. If you go to, chapter 4 over there, you will find out that add should be encoded this way. I'm going to show you a picture of that later. But it basically consists of these different fields. I'm going to give you examples in a little bit. But you can tell, if you know the fields, this opcode specifies it's an add. This is source register 2 is register 2, source register 1 is register 1, and destination register is 0. So there are particular fields in the 16-bit encoding over here that basically tell you what parts of this encoding indicate the registers and what parts of the encoding indicate the operation. And of course, you can write this in a bit more nicely with exact 16 bits. It looks like this. And these are the different bits, bit 0 over here, bits 15 over here. And the top 4 bits always specifies the opcode, which is what you should do, what the instruction should do, should make the machine do. We're going to talk about that also. And this is the short format. This is basically the machine code. If you want to do it in hexadecimal, it's 4 4-bit values, because LC3 has 16-bit instructions. Okay, we're going to go into a little bit more detail, but that's how you go from assembly to machine code. So basically, how is this thing defined? This is defined by the instruction set architecture, and it's called the instruction format. In LC3, instructions look like this. At least the operate instructions look like this. You basically have the opcode and the top 4 bits of the 16-bit word in memory that specifies an instruction. And then you have the destination register in the next 3 bits, source register 1 in the next 3 bits, and source register 2 happens to come from the bottom 3 bits. This is an encoding, basically. When the machine gets this, it basically looks at these different parts and says, oh, I have the opcode. It's saying 0000 or 0001, so oh, it must be an add. There's a contract between the software and the hardware. And the destination register is specified by these 3 bits, the source register is specified by these 3 bits, and source register 2 is specified by these 3 bits. So I should add source register 1 to source register 2 and put the result into destination register. So opcode specifies what the instruction does, what should the machine do when it actually has this instruction in the instruction register. Add is encoded this way, and is encoded this way, for example, in LC3. SR1 and SR2 are source registers, and DR is the destination register. For example, add semantics is add SR1 and SR2, store the result in the destination register, and is basically similar. And is a bitwise AND. Basically do a bitwise AND of SR1 and SR2. Okay, so MIPS is very similar, basically. I'm going to go through the MIPS also. Basically, all ISAs have similarity, except they also have idiosyncrasies. So MIPS is 32 bits. Instructions are 32-bit values. So that's why you have these different parts. In this case, you can also see, if you delineate these values, you can see that we're adding register 17 to register 18 and putting the result into register 16. Even though they're called S0, S1, S2, remember that table that I showed you earlier? In MIPS assembly language, they correspond to these registers. And then function specifies what you actually need to do. Basically, if you are a machine, you would interpret this as, I should add RS to RT, put the result in RD. This is the machine code, full 32 bits, very similar to LC3, but of course it's slightly different. And this is really the hexadecimal machine code. Okay, so let's go into a little bit more into instruction. We're going to cover different types of instruction. So this is also called an R-type instruction MIPS. It's called the register type. It basically has 3 register operands, 2 source registers, 1 destination register. Basically source registers are specified by these 5 bits over here, 5 bits each. Destination register is specified by this set of 5 bits. 0 is the opcode, which basically tells you that you should really look over here, which is one way of encoding, right? RS and RT are source registers, and RD is destination. I said that shift amount, there's this thing called shamt over here. That's the shift amount, and it makes sense only for shift operations. And we're not going to cover shift operations right now. You can cover them on your own. This function is actually what's really telling you what you should do. This is really the operation type in our type instructions. So if you see opcode 0, you know that the encoding looks like this, and you basically go and figure out the function that you need to do over here. So add has a specific encoding over here, and has a specific encoding, nor has a specific encoding. Okay, basically with operate instructions such as addition, we tell the computer to execute arithmetic computations or logical computations in the ALU. So we also need instructions to access the operands from memory, so we will see how we read and load from memory. And writing is stored in a similar way, but we will see that later. So again, I'll start with the high-level code. This is an array access, for example. We're going to assume word addressability, and then we're going to move to byte addressable very quickly. Basically, let's assume that I want to address the ith word at array A. This could be an assembly, but it's really not the assembly because you normally don't put A's directly over there. But we will see the exact assembly soon. So load is the mnemonic in the assembly to indicate the load word operation. A is the base address, and I is the offset. Basically, it's the immediate or literal. It's a constant from the base address of the array. And A is the destination. Basically, it's the register that you're going to move this word to from memory. And the semantics is basically access memory at address A plus I, get the word out of there, and place the word into this register A. Okay. Now let's take a look at, assuming that LC3, and we're going to imagine a machine that's word addressable, but MIPS-like, how would you do it? So this is the high-level code. In this case, I'm going to make it concrete. Let's say we want to access a word at offset 2 or index 2 from array A. So this is the assembly. So assuming that your array starts from R0, let's say address 0, you basically go to word 2, that's the index indicated by this immediate, this LDR. So assuming that the beginning of the array address is in R0, you take the value is in R0, you add to it 2, and you calculate the address. That's the idea basically. And you calculate the address, and you access memory in that location, and put the value in R3. This is one way of accessing memory, and this will become more clear. So MIPS is going to be similar. It's basically like this. So you can see that the syntax is a little bit different, but it's essentially doing the same thing. Use the value in the register S0 as the beginning address of A, add 2 to it, access the word in memory, put the data into register S3. Okay. So basically, these instructions use a particular addressing mode. This addressing mode is called base register plus offset. It's called base plus offset or register plus offset. You can see both. So the addressing mode is how you do calculate the address that you're addressing in memory. So now I cooked up something over here. This is the word addressable MIPS. But there's also a byte addressable MIPS. So the byte addressable MIPS is what we're going to look at over here. So MIPS is really byte addressable, so we really need to use 8 over here. If this is our high-level code, if array A contains elements that are words, the second element, second offset, 0, 1, 2, really starts from byte 8, right? Because you have 2 words, each of them has 4 bytes, so this second one should start from byte 8. And that's exactly what this MIPS assembly that corresponds to this says. Get the address by calculating the base address of the array, which is in register S0, add 8 to it, which is that, access the memory location, and then put the word that you get from there, because it's a load word, into register S3. So how do you calculate the byte address? I just told you. More formally, you take the word address, which may be in your array. So at the high level, programmer is operating on words. It could be operating on something even bigger. Then you need to multiply it with something bigger, right? It could be like 64 bytes, right? If you have that data type in your language. So basically, you multiply the word address by bytes divided by word. So you have 4 bytes per word in MIPS. So so that's why we multiply 4 by 2 over here. If LC3 were byte addressable, then you get 2 bytes per word. Okay, so this is essentially instruction format with immediate. So what we did was we have an immediate value over here that is part of the address calculation. And this is what the encoding format looks like. Basically, the top 4 bits always designate the opcode in LC3. In this case, LDR happens to be encoded with 6. Once the machine sees 6, it looks at a format that looks like this, basically. And the format is such that the base register is specified by the value that's over here. The offset is specified by these 6 bits over here. And the destination register is specified by these 3 bits over here. So once you see the opcode, you know what the rest should look like because there is an agreed upon format of instructions between the software and the hardware. Okay, so if you look at MIPS, it's also very similar actually. It's called an I-type instruction MIPS because this is an immediate value over here. Essentially, you have the opcode. Once you see this opcode, the rest of the instruction looks like this, instruction bits. So this is your source register, this is your destination register, or the other way around actually. Yeah, exactly, that's true. This is your destination register and this is the immediate. So it's a little bit swapped over here, as you can see, destination register over here. But it basically is a format, it's a convention that's agreed upon. If you're building an LC3 machine, you should make sure you obey this format, right? And if you're writing a program for LC3 machine in machine code, you should make sure you obey this format. Okay, so that's encoding. So now how are these instructions executed? I was kind of talking about execution also, but let's talk about how you can, once you see this encoding of an instruction, how can you execute it? So basically using instructions, we're really speaking the language of the computer at the lowest level, right? So we know how to tell the computer to execute computation in the ALU by using, for example, an addition, or access operands from memory by using the load word instructions. But how are these instructions executed on the computer? As I said briefly earlier, the process of executing an instruction is called the instruction cycle. Not to be confused with the clock cycle. Clock cycle is very low level. It basically is how fast your clock is your clock, right, as we discussed. Instruction cycle is the process that you have to execute an instruction from the beginning to the very end. And what is that instruction cycle? Basically, an instruction cycle goes through a sequence of steps or phases to get executed. And these are the 6 phases. You need to first fetch the instruction, decode the instruction, figure out what it's doing, evaluate the address of the instruction if the instruction needs an address, fetch the operands that the instruction is supposed to operate on, you need to execute the instruction and store the result of the instruction somewhere. Okay? And all instructions go through these steps, not all of them go through every step or phases. I'm going to use phases and steps interchangeably. For example, if you're loading, if you saw the load earlier, base pulse offset, it's called LDR, load register. It doesn't execute because there's nothing to execute. You're just loading some data value from memory into a register, right? You don't go through the ALU, arithmetic logic unit. This is a simple load of a data value from memory to a register. You need to calculate the address, evaluate the address, but you don't need to execute anything. After you fetch the operand, you directly store the result into the register that's specified as the destination register. Add doesn't need to evaluate the address in the machines that we're looking at because add actually doesn't have an address because the operands are encoded in the registers, right? There's no memory address that it needs to evaluate. Okay, there are other more complicated ISAs that actually go and read a memory location, add it to a register, and write the result back to a memory location or to a register. x86 is one example of that ISA. It's more complicated. So you can actually do, one operand can come from memory, another operand can come from a register. You do the calculation, and you may store the data into a register or memory location, depending on the instruction. This goes through all of the 6 phases, actually. You need to do every single step, but it's a more complicated instruction also. So the instruction set architectures we're going to examine are register-to-register architectures. You basically don't have operands coming from memory. You cannot operate on those operands. You basically operate only on the registers. If you want to operate on a memory location, you need to first load it into a register and then do an ALU operation on it. Okay. Is this clear? So now we're going to go through each step. So pay attention because it's going to be important. We're going to use this for the rest of basically the course, because every instruction in every machine is executed this way today. Basically, it's a loop. You fetch the instruction, decode, evaluate address, fetch operands, execute, store results, and then go to the next instruction. And then you keep doing this forever. Your computers are running loops, basically. Okay, let's take a look at what the fetch phase does. So fetch phase obtains the instruction from memory and loads it into the instruction register. We actually saw this step. I'm going to go through this in a little bit more detail. It's common to every instruction type. Basically, your program counter indicates which instruction to fetch, and you go and fetch it. You fetch the instruction encoding into the instruction register. So basically, you load the memory address register with the contents of the program counter and simultaneously increment the PC, because you need to go to the next instruction anyway, later. And then you interrogate memory. This results in instruction to be placed in the memory data register. And once the memory data register has some value in it, you load the instruction register with the contents of the memory data register. Make sense? So basically, this is the step where you're accessing memory, and this is the step, once the memory responds, you get that data value and put it into the instruction register, because you're interpreting that data value in that memory location specified by the program counter as an instruction. That's very simple. So let's take a look at how this is done in this machine. So basically, the first step is to load the MAR, memory address register. We'll get to the increment PC later on. So basically, in the first cycle, what you do is you basically gate PC, set this to 1, set all of the other gate signals to 0, and the data gets loaded, it flows, and it gets latched into the MAR at the end of the clock cycle. So this is our finite state machine. That's the thing that the finite state machine needs to ensure in the first clock cycle if you're fetching. That's the fetch state. So a fetch state will be a particular state in our finite state machine that controls all of the operation. That's the control unit, okay? So what this did, the PC got captured in the memory address register. That's good. In the next cycle, memory access starts. But before we do that, we can also increment the PC, because we eventually know that we're going to go to the next program counter, right? And to be able to do that, there's an element in the data path over here that basically has an incrementer, PC plus 1, and you select that one. You set your control signal so that in the first cycle, in the fetch, in the first cycle of the fetch stage, the PC mux selects this input, and you enable the load PC. Now, there's concurrency happening here, right? While you're getting the old value of the PC into MAR, you're also changing the value of the PC, but both of them are happening concurrently. The value of the PC doesn't change until the end of the clock cycle. This is our principle in sequential finite state machines, right? We have a flip-flop, and as a result, the new value gets latched only at the end of the clock cycle. So during the clock cycle, you're incrementing the PC, and the new value gets latched at the end of the clock cycle. While that's happening, you're also putting the value of the PC into the MAR. Okay, that's the first step. So done in one clock cycle. Next clock cycle, you access memory. Assuming that memory access takes one clock cycle, the data appears in the next clock cycle in the MDR. If the memory access takes 5 clock cycles, you basically wait for 5 clock cycles, right? You need to have some mechanism to wait for 5 clock cycles. And at the end, the data is here, and you can start the third step, which is basically taking the data, loading into the bus, and putting into the IR. How do you do that? You set this signal to 0, and you set the signal to 1, such that during that clock cycle, the data that's coming from over here gets written into instruction register. Okay, so now you kind of have a sense of how you should set the control signal so that the elements that are designed do the things that you want them to do. And in this case, we're fetching an instruction. We don't even have an instruction yet. We're fetching the instruction from the address pointed to by the program counter into the instruction register. And that's the third step, basically. You need to ensure in every clock cycle, the control signals are set appropriately to obey the specification that I just said over here. And how do you ensure that? You build a finite state machine that does it. And you know how to build finite state machines by now. Okay, we'll see the finite state machine later. So the next step is decode. The decode phase essentially identifies the instruction, right? So how do you identify the instruction? Basically, we have a decoder. Remember? Actually, if you don't remember, you can go to the slides. In LC3, you have, remember the opcode bits are 4 bits, top 4 bits. You can run those 4 bits through a decoder, a 4 to 16 decoder, it identifies which of the 16 opcodes is going to be processed. Remember, when I introduced the decoder, I said it's a pattern matcher. Opcode is a pattern, 4-bit pattern. You want to figure out what that 4-bit pattern is and raise the right signal saying, oh, okay, this is an add, this is an AND, this is a load register, different types of load, this is a NOT, this is an XOR, okay? So basically, LC3 has 16 instructions decoded this way. And the input is, as I said, it's already in the instruction register. These are the top 4 bits of the instruction because you already placed the instruction into the instruction register. The remaining 12 bits identify what else is needed to process the instruction. And we know, based on the format encoding, that different instructions have different encodings, and these bits specify what you need to do, and we will see that. Okay, so how does decode happen? Basically, you already have the instruction in the instruction register. You basically need to identify, decode it. And decoding means that you go through some decoder, and that's the decoder over here. These are the 16 bits over here. Well, you decode this and you figure out basically what instruction you have by looking at the top 4 bits. Okay, there's more to discuss on the decoder, but we'll do that later. Decoder also identifies which part of the instruction are denoting the source registers and the destination register. All of those are the outputs of the decoder. Like, what is your source register 1 ID? What is your source register 2 ID? What is your destination register ID? If you have an immediate, what is that immediate? If you have a shift amount in MIPS, what is that shift amount, for example? Okay, so the next phase in the instruction processing cycle is evaluate address. So evaluate address phase computes the address of the memory location that is needed to process the instruction, assuming the instruction needs a memory location address. So this phase is necessary in load register that you saw, LDR. So it computes the address of the data word that's to be read from memory. In this case, the instruction specifies the computation of the address such that you add the offset, or the immediate, to the content of a register. That was LDR, if you remember. But this phase is not necessary in add, because add doesn't, in LC3, doesn't require access to memory to get its operands. Okay, so how does this work? Basically, LDR calculates the address by adding a register and an immediate. So decoder told us what is that register, source register. Decoder also told us what is that immediate. So this is not shown here, but what happens is you access the register file, get the source register value inside from the register file, and add to it the immediate value, actually a sign extended version of the immediate value over here. You'll see this in more detail later on. So you have a special adder over here that has the address over here. So now we have the address. Yes?
You said LC up to or add structure so if I want to add number to this portion and we go first.
Exactly. You first need to use a load instruction to put the values in the register, and then you do the add. Exactly. Basically, you're only capable, your capability is dependent on what's in the instruction set. If you don't have the instruction to do it, you use the smaller instructions to build the larger constructs. Okay, so this is LDR. You'll become familiar with this more and more. So the next step is fetch operands. Basically, it obtains the force operands needed to process the instruction. So in LDR, for example, this is very similar to actually, in LDR, this is very similar to accessing memory. We're going to access memory. We already access memory in the fetch stage, but we use the program counter as the address. Now we're going to use the address that's calculated in the evaluate address stage and load it into the MAR. And then we're going to read the memory, which places the source operand into the MDR. And then in add, you obtain the source operands from the register file. Okay, so in most microprocessors, this phase can be done at the same time the instruction is being decoded, but you can ignore that for now. So let's take a look at it. So remember that we calculated the address in the LDR. So you have the address, and you need to load it from the bus into the MAR. Right. Now the address is here, and then memory placed the results in the MDR, and now the data can be written back. We will see that later on. Okay, so the next stage is execute. After you get the operands, you can execute. In add, basically, you perform the addition in the ALU. Right. So it's very simple. Add, if you want to add SR1 to SR2, you see that there's an SR1 input, SR2 input coming from the decoder over here because you have the instruction register of the instruction that you're executing. And basically you have the elements coming from the register file, and the result of the ALU is now here. Right? Okay. And the last stage in instructions that write to some place is called the store result stage. Basically, this phase writes to the designated destination. So once this is completed, a new instruction cycle starts with the fetch phase. So let's take a look at this in the case of LDR, for example. You have the data in memory data register. If you're loading, you basically take that and place it into the destination register in memory. Destination register in the register file, sorry. So to be able to do that, again, you need to set the control signals appropriately. This gate MDR should be 1 so that you load it, and all of the other gating signals onto the bus should be 0 because nothing else should really transmit on something onto the bus. Now if you load MDR or gate MDR onto the bus, it flows, it comes here, you have a destination register, you need to specify that, but that's already specified with the instruction that you're executing, that's LDR, it's coming from the decoder. And you need to have a write enable signal over here, which is the load register signal here. That you need to enable so that the value that's flowing out of MDR, because you set this to 1, goes into the destination register that's specified by DR, because this is set to 1. Okay? So by orchestrating the control signals appropriately, using the finite state machine, you can ensure that the instructions do what they are supposed to do. And we'll see more examples of this later on. But recall this instruction cycle all the time. Okay, so one thing we have not discussed so far, we've discussed some examples of add, example data movement instruction. We have not discussed control flow instructions. Let me discuss a little bit. Basically, I mean, I already said this. There's a sequential execution that we're assuming with the von Neumann model. This is what you do normally. You basically go through instruction by instruction, and instructions are sequential in memory, unless you change the sequence of execution. So control instructions allow a program to execute out of sequence, and this is useful if you have an if-then-else construct, for example. Right? So what do these control instructions do? They can change the program counter by loading it during the execute phase. So what this does is that wipes out the incremented PC, because in the fetch phase, we incremented the PC, right? Assuming that we're going to the next instruction. But in the decode phase, we figured out the instructions, the control instruction is going to change the program counter. In the evaluate address stage, that instruction evaluated the address that should be loaded onto the PC. In the execute stage, they can load the PC program counter with the address that they evaluated. Right. That's the idea. Let's take a look at one example, one very simple example. It's called a jump. It's also called an unconditional branch or unconditional jump. Unconditional means it's not testing a condition. Unconditionally, whenever you see the jump instruction, you're going to go to the address specified by the jump instruction. We will see why this is useful tomorrow. So this is one example. Jump to the location that's specified by register 2. Register 2 has a 16-bit address in LC3. Jump to that memory location. Okay, this is called jump register. This is a register addressing mode. This is the encoding, as you can see. As you can see, the opcode is 1100. So that's basically it. I already said this. It's called the register addressing mode. So there are variations of this. There's a return instruction, which could be useful whenever you're doing function calls, for example. It's a special case of jump where the base register is R7. So you don't really need this instruction, actually. And there are also jump to subroutine instructions, which we're going to see tomorrow when we talk about function calls. Jump in MIPS is very similar to x86, not x86, LC3, except the target address calculation is a little bit different. This is a jump immediate addressing mode. So basically, the target address is encoded inside the instruction itself. You don't go to a register to get the target address where you should jump to, where you should change the program counter to. It's encoded inside the instruction bits, because instruction bits are 32 bits, 26 bits are used for that purpose. And these 6 bits, if they're 2, you know that it's an unconditional jump instruction. That's the opcode, basically. This is a special type. It's called the J type, jump type instructions. Opcode is 2, target address is specified by that. And the target address computation is a little bit more complex than just taking this target address. Basically, you take the program counter's top 4 bits, sorry. That's what this indication is. And you need to be careful because this is really the incremented PC. It's really not the program counter of this instruction, but program counter of the next instruction. That's by convention again. This is basically that. And then you concatenate those 4 bits with these 26 bits multiplied by 4. What does that mean? You add 2 zeros at the bottom of the 26 bits, because multiplying by 4 means shifting left by 2. And you concatenate that value to the 4 bits of the PC. So it's a little bit cumbersome, but you basically take 4 bits and 28 bits over here, you put them together, and that's your next program counter. So this is how you can calculate your address. So if you know you want to jump to some instruction, you need to calculate what target you should put into your instruction if you're doing this machine level coding. Of course, most people don't do that. The compiler figures out which target bits to put in an instruction because it knows where should the program jump. Okay, this is another addressing mode. The address is calculated using pseudo-direct addressing mode. You don't have to remember that. So there are a bunch of variations. Jump and link is useful for function calls. We'll see that again. Jump register is actually what I showed you earlier. This is the jump in LC3. It's basically you jump to the location that's indicated by the 32-bit value in the register S0 in this case. Right? Basically, PC gets that value. Okay? So there are variations basically so that you can do different kinds of jumps. And this is the register addressing mode that's very similar to what I showed you earlier. Okay, so let's take a look at how this happens in the LC3 data path as well as some other stuff. Yeah, actually, yeah, how do you implement jump in LC3? Let's take a look at it. So we're going to look at, this is our program counter over here. So we already discussed gate PC. But if you want to actually implement jump in LC3 to a register, during the execute stage, what needs to happen is you take the source register and basically load the program counter with it. That's it. Makes sense, right? So there needs to be a path taking the source register here. You set the control signal during that time so that you select this input, and you ensure that load PC has value 1. You enable that flip-flop so that PC gets written. And the value that's coming out of source register 1 gets placed into a program counter. And we can look at these later on. Okay, makes sense? So basically, I think I've covered a lot of the instruction cycle, but this is a small introduction of to the finite state machine that I kind of was describing to you. Basically, this is the fetch part. So you have 3 states, assuming memory access takes 1 cycle. This is what you do. In the first state, you load, actually I'll do this. You basically, the finite state machine asserts gate PC and load MAR, so that PC gets loaded into the MAR. Imagine the picture right now. And PC also gets incremented at the same time. It selects input +1 in PCMux and asserts LDPC. You should go through this on your own. We've gone through a lot of it actually so far. And then you go to the next state. At the end of the clock cycle, you transition to the next state. And the next state, you're basically accessing memory. MDR is loaded with the instruction. Well, we know that it's an instruction in this case because we're in the fetch states over here. We designed the finite state machine. Now at the end of that state, we have the instruction in the MDR. In the third state, we move that instruction or the data that we got in the MDR into the instruction register. So you need to assert the control signals that are necessary to do that movement, which I've already told you actually. You gate the MDR onto the bus, and you load the instruction register, and whatever you gated from the MDR goes into the instruction register. And then the next state is actually decoding, if you look over here. And basically the FSM goes to the next state depending on the opcode. If you look over here, there are 3 kinds: add, LDR, jump. But actually there are 16. This is just the things that we've looked at so far. If the opcode is an add, you go into this set of states. If the opcode is an LDR, you go into this set of states. If the opcode is a jump, you go into this set of states. So now actually, we're building a machine that can execute 3 instructions, as you can see, right? It can fetch any instruction, it can execute 3 different instructions. If you want to execute 16 instructions, you need to have a 16-way machine. So let's assume it's a jump, you decoded it, and that's the first state for after decode for the jump instruction. So you do something, that something is clear in that book. And then at the end, you have this state where the register that you read gets loaded into the program counter. Now your program counter changed to the address that was in the register that was specified by the jump. Now where do you go next? Well, this says to state 1. We've changed the program counter such that the next instruction that's executed will be fetched from that program counter. We've jumped to some other location in memory, basically. Now, if you actually executed add, you would have done the add, and then you would go back to state 1. Right? Okay, so that's the finite state machine. And if you want to have the full state diagram, it's in Appendix C. Okay, so now let's go through the instruction set architectures in a little bit more detail. And then we're going to go into a little bit more, and then we're going to cover programming tomorrow. So what's the instruction set? And you've seen all of this, actually. So it defines opcodes, data types, and addressing modes. And we've seen add and LDR as our first examples. So add is like this. You've seen this. LDR is like this. This is the specification. Add uses register mode. This is the base plus offset mode for how it calculates the address, right? These are just registers. This is actually register plus offset or base plus offset. So I've already said this, but let's make it more clear. The ISA, instruction set architecture, is really the interface between the software commands and what the hardware carries out. What the programmer should expect, the hardware should do. And that's the ISA. It's basically the link between program and microarchitecture. And we've seen a lot of microarchitectural logic over here. Now we're going to link it. Actually, we've linked it, but now we're going to make it a little bit more formal. So it specifies the memory organization, which we've covered, address space, addressability, word or byte addressable. That's part of the ISA. It specifies how many registers you have. The programmer needs to know that. It specifies what are the instructions, what are the opcodes, what are the data types, what are the addressing modes. Basically, everything is specified so that the programmer can write the program that the hardware is going to execute. Right? It's a contract between the hardware and the software. If you have a machine that executes ARM ISA, you have a contract, you have this contract written in a book. That book tells you, okay, these are the properties of the ISA: memory, register set, instruction set, right? And a bunch of other stuff also, which we won't get into right now. So opcodes could be many or small, right? For example, there's an opcode instruction for doing this in one of the architectures. x86 has different instructions. I said earlier that it has a binary coded decimal instruction, right? x86 has multimedia extensions, later called SSE and AVX, which we're not going to go into. In the VAX ISA, which is an old ISA, it's a dead ISA, nobody uses this ISA as far as I know right now. You have instructions that are much more complicated. For example, you can save all the information of one program prior to switching to another program, all the registers. This single instruction does this. So instruction capability varies depending on that contract, that book that you get. Okay, this is the processor that I have. What can I do with it? What is the capability of the instruction, right? So there are trade-offs are involved in the design of this, like what should be the opcodes, hardware complexity versus software complexity. For example, if you have very complex opcodes, operations to be done by the program, then hardware becomes more complex. Maybe a software's task is easier. For example, you can write a linked list access, linked list node access with a single instruction. That's possible in some particular ISA. Not in MIPS, not in LC3. Not in most ISAs, actually. Because hardware becomes more complex and software may be easier, but compilers are very good today, actually. So maybe they don't want the linked list instruction. Okay, so in LC3 and MIPS, there are 3 types of opcodes, as we said: operate, data movement, and control. And this is the opcodes in LC3. So this is actually the full ISA in LC3. And the opcodes are always at the 4 top bits, right? And you can see the different formats of the instruction. This is a full specification of the instruction encodings in LC. I shouldn't say full ISA, because ISA includes other stuff like memory and registers. But this tells you the instruction encodings. This is LC3B. It's a little bit different. It has a different instruction. It has XOR. Turns out it's nice. And it has 2 unused slots. If you want to add some other instruction, maybe later you can augment the ISA with the specification. And this is another example for MIPS R-type instruction. MIPS is much more complicated, so we're just looking at the R-type over here. You don't need to memorize this. Whenever you go through this, you actually figure out how it works. So basically, for example, opcode is 0 in MIPS R-type instruction, and funct defines the operation, as I said earlier. So where is that funct? Funct is this. This is the function, basically. They didn't have enough characters to write ION. That's why it's funct. Okay, and for example, these are the other instructions. So it doesn't fit over here because it has 6 values, 2 to the 6 is 64. So you have some other page over here. And you can find the complete list in the appendix. So this is actually a very good place to stop. We're going to continue with the ISA tomorrow, and we're going to do some programming, assembly programming. I'll see you tomorrow.